We are investigating the photoelectric effect, and I showed this crude drawing of this apparatus here. Essentially, it's the same as our applet. Our applet shows an electrode on one side that's covered in our target metal, the metal that we're interested in. And I think the applet actually defaults to sodium, so sodium might be the metal here, say. We shine light with minimum frequency of the threshold frequency onto that metal surface. And what happens is, of course, the metal surface emits electrons. And those electrons, because this is a semicircle, it should be parabolic and have a focus, theoretically. But your book says that it's a semicircle and the focus is kind of this electrode here. Those electrons will tend to mostly go towards this electrode. When they strike the electrode, they essentially allow a current to pass through this circuit here. And so we can read that current. It's a very small current, so we use a microammeter. And we can vary the potential difference. You'll remember there's a reason why we have a potential difference here. We start off at 0 and all the, so 0 volts, all of the electrons that leave that metal surface strike the electrode on this side and create a current. As I increase the potential difference here so that the electrode here is more electronegative and this side where the metal surface is more electropositive, the electrons will get so far depending on their energy and then turn around and go back. They may still make it if they've got enough energy, but they may not also. By varying this potential difference, we can actually work out how much energy those electrons have upon leaving the metal surface. It's a way of measuring how much energy they have. That's all we want to do by varying this potential difference. And we know that if the potential difference is 1 volt, so we have a negative side and a positive side, and the potential difference between those two electrodes is 1 volt, and the electrons that travel from the metal surface to the electrode, if they just make it, at the point at which they're just making it, then those electrons have 1 electron volt of energy. Okay. Of course, we're interested in the energy, the maximum energy that those electrons have, and the maximum energy is related to the electron charge, which is, this is, of course, just, hang on, let me get a different color here. That's the electron charge. Or 1.6 by 10 to the minus 19 coulombs. And can anybody remember? Oh, it's right, written right here. It is. This is a stopping voltage. Can anybody describe for me what the stopping voltage means? Stopping voltage is that moment, or rather, that potential difference at which the electrons just don't make it to the electrode. Okay? The moment at which we read, because we can't see those electrons in a real setup like we can in the applet, but we can see that the electrons are arriving at this electrode here by the microammeter. If it's reading a current, then the electrons are making it across. At the moment where it's reading a current and then we turn up this potential difference and then it's not reading a current, that's the stopping voltage. That's the moment at which we manage to stop the electrons from reaching that electrode. And the stopping voltage is related to the maximum kinetic energy of the electrons. Because if you remember from the applet, if I bring up the applet, did I open that? Oh, yeah, I did. If I bring up the applet and we give it some intensity, we're in our within our threshold frequency range here. Of course, this is read in wavelengths. You can see that these electrons have different energy levels. They have different speeds. And so in order to find out the energy of the most energetic electrons, of course, the electrons that are least energetic don't make it as soon as I turn that potential difference up a little bit. But the most energetic ones do. And if I turn it down so we just don't have a current, and it's very hard for me to manipulate this toggle here using what I'm using here, but if I can get that moment where they just don't make it, the most energetic electrons. So we've still got a current there. 1.6 is going to be too much. If I type it in, this is the best way to do it, I think. Let's try 0.8, minus 0.8 volts. You have to press enter. Yeah, okay, so it's showing a current of 0, so the electrons aren't making it. The most energetic electrons aren't quite making it. In fact, it's not minus 0.8, the stopping voltage. It's somewhere in between 0.6 and 0.8 volts, minus 0.6 and 0.8 volts. So, and you have to find that stopping voltage by typing in the numbers here. The moment at which the current reads 0 and between the moment where the current starts reading is the stopping voltage, that moment at which the most energetic electrons don't make it across the gap. Okay, let's explain that a little bit. So work function, we define work function as well. Minimum energy required to remove an electron. Now, what we're doing is we're sending photons or packets of energy into this atom. I don't like this model of the atom. It's the Bohr model of the atom, and it's this idea that we have these. Well, it shows that we have discrete energy levels around the atom, which is true, but it's not a good representation of what's going on around the atom. But to remove an electron from the atom, we've got to add energy to that atom, of course, or some people might say to kick off an electron, we have to give energy to an electron so that it becomes free from that atom. And what we say is these electrons have negative energies. That is, that they are bound to this positive nucleus through their negative energies. And what we have to do is raise, through shining light on it, the electron's energy to 0. And then it becomes a free electron. If we only raise it to 0, then theoretically it's got no energy, which means it's not moving. But anything greater than that, then we'll have electrons that leave with some velocity v from this atom, free from this atom. Okay, so work function, one more thing about work function. This is the energy. It's an energy required to remove the most energetic electrons from an atom or a metal. We could call it a metal, or we could call it a substance. And we had a lot of discussion about what the, actually I'll go to a new page, I don't like this Bohr model atom, but what I prefer, in fact, is an energy level diagram. And if I draw some energy levels in, this might be a particular material. Okay, and the most energetic electrons, they might have minus 20 eV of energy binding them to that nucleus. This might be minus 15 eV. We call these jumps between energy levels transitions. So this could represent a transition from minus 20, or this energy level here to this energy level here. That's supposed to be an arrow there. And that can only occur if we give the this atom some energy. And we do that by shining light on it. For that jump, for that transition to occur though, that photon to be absorbed by, and you could imagine like there's an electron here. You could imagine this is an electron jumping from one energy level to another. Oh, hang on. What am I doing? This is... Yeah, so this is a photon here. Actually, I won't do that in blue. Quiet, please, boys. Thank you. Photon. That photon, that electron, in order to accept this photon and make this transition, that photon must have 5 eV, almost exactly, of energy. Has to be, for that transition to occur. However, and this is something that we could have a different transition occur. We could have a transition happen where, and the photoelectric effect, or the definition of the photoelectric effect so far as what we've been seeing, is we could have an electron here at minus 20 eV, and we give it enough energy to become a free electron, and then what it does is, of course, with its energy, it goes off and reaches the target. Okay, so we might have the electron moving off with some energy. How much energy do I need to give it here to become this moment where it's free? Yeah, well, minimum 20 to become free, so that it becomes 0 eV of energy here, but we've actually given it more than 20 eV of energy with a photon. So that, yeah, it could be any number, 25, let's say. And so when this electron becomes free, it's still got a little bit of energy to move off at some velocity v. And that might be, if you give it 25, then it might be 5 eV electron. And that's how we would describe an electron. We would say about its energy level. That's a 5 eV electron. Okay. Of course, I could measure that practically using the apparatus that I've described. How could I measure that? Rung? How could I measure it? If I'm firing in photons with 25 eV of energy, and I know that the atom, the work function of this atom, because this is just an atom here, this is an idea of an atom, it's an energy level of an atom. If I fire in 25 eV photons, and I know that there are approximately 5 eV electrons coming off, but I needed to measure that for sure. Using the apparatus that I've described for you before, how would I measure that energy? Using the what? Microammeter and the voltage, yeah, the variable potential difference, wouldn't I? Because I know if I've got electrons, say this is our metal surface here, and this is the electrode, and I should have drawn that in a different color. I have electrons moving across this gap here. Let's change this color. Okay, this is an electrode. This is the other electrode, and they're connected via, they are a circuit. if I want to measure how much energy that electron has, all I have to do is say, okay, what if this is more positive and this is more negative? How much energy does that electron have to make it across there? Depends on this voltage, doesn't it? And if it's 5 volts and the electron just doesn't make it, it turns around and comes back, then I know that it has 5 eV of energy. Okay? Moving on. There's some examples here. Sodium, when you use the applet, I think the applet actually uses this. This is a documented sodium work function. Is approximately equal to minus 2.46 electron volts. And we would just say that as the modulus. So we need 2.6 eV to make those electrons become free. Copper, 4.7 eV. Einstein won his Nobel Prize for this, for describing this. He was a theoretical physicist, and he's described how this works exactly. He didn't get it for relativity, which is a common misconception. We know several things, and I'll just read them out because we have spoken of these before. Um, 1905, Albert Einstein published an explanation of the photoelectric effect using a concept of light as a stream of photons or packets of energy. Remember, they are not particles as such. These are his assumptions. When light is emitted, it is not emitted as a continuous wave, but as discrete bundles of energy called photons. They behave such that their energy is equal to Planck's constant multiplied by their frequency. The intensity of the radiation is proportional to the number of photons crossing a unit area per unit time. So more photons, more intensity, essentially. When a photon collides with an electron, it may transfer its energy to the electron. Such transfer of energy is instantaneous. If such a transfer of energy occurs, the photon gives all of its energy to the electron. It cannot transfer just part of its energy. Okay. Now, do I want to... Oh, yes, this is the formula we need to go to next. Using E equals HF, we know the threshold frequency as this minimum energy, F sub 0, minimum energy required to remove an electron from an atom. So the minimum energy is equal to Planck's constant multiplied by the threshold frequency. And from our definition of the work function, the minimum energy is also equal to the work function of a particular material. So this depends on the material. Note that this value here, the work function, is calculated by this. Okay, so I've just said that the minimum energy, which is also the work function, is equal to Planck's constant multiplied by the threshold frequency. What about if we do this now? We have some metal surface, whatever it may be. We shine some light on it. And that light has several different frequencies. Okay, so I'm just doing some different colors to say that it's got different frequencies. Now, that light of different frequencies being minimum the threshold frequency, of course, then we're going to have electrons ejected. But what sort of electrons are we going to have ejected? Well, firstly, we're going to have these minimum energy electrons, but we're also going to have these higher energy electrons as well, because we've got different frequencies going in. Okay, different frequencies results in different energies of electrons. If a photon collides with the metal, it needs to give the metal how much energy in order to emit just the what's the basic amount of energy, the basic amount of energy that a photon needs to give in order for one of these electrons to be ejected? Equal to the work function of the metal. So it needs to give the metal to eject an electron the photon must give minus the work function to the metal. Okay, so but these photons have energy E equals HF. So you can see that the energy that one of these electrons have, E equals HF minus the work function. The energy of this electron that's ejected is equal to the photon energy, the original photon energy, minus the work function of the metal. The electron will be the one that is emitted with maximum kinetic energy K, as it had to use up the least amount of energy to leave the metal. This is Einstein's photoelectric equation. I'll say that. Give some credence to Einstein. The maximum kinetic energy is equal to the energy of the photon minus the work function of the metal. I think we can go into a problem now. We haven't done an example yet. Before we do, there's a couple of graphs that I need to show you, and I have shown you these graphs before. These are energy frequency graphs. So we have a graph like this. Here we might have the kinetic energy, and here the frequency. Now this kinetic energy, though, can be described in EV, of course, or in joules. And you need to know the difference between the two. You need to understand how to convert these. Kinetic energy in joules. And this is frequency. This is still hertz in both cases. The graphs look very similar. And we know what a graph is going to look like. It's actually going to look like this. This might be a different type of metal here. Something like this. The slope of this graph will be what? This could be metal. Metal A, metal B. So on and so forth. The slope of the graph, K max, is equal to HF minus omega. What's this? Mx plus C. Y equals Mx plus C. The work function is where the graph strikes the y-axis. So slope of the graph is h. Should be this number. And when we're talking about kinetic energy, we generally, when we do any calculations, it's always with the result as joules. If you're asked to do the calculation in EV, then you just do this. So the kinetic energy equals HF minus omega, minus W, sorry. In EV, Planck's constant for the left-hand graph, for this graph here, okay, or the slope of the graph, Planck's constant h is the slope on the right. On the left graph, we have slope equals to h on the electron charge. Still a problem. So the work function W of copper is 4.7 eV. A copper surface is irradiated with lights of different frequencies. Sketch a graph of the maximum kinetic energy of emitted electrons against frequency of the light. You only need to know two values here, and I think most people could probably draw the graph. Have a go at that, please. At least begin to draw the graph so that when I do fill it in, you can... If we were to draw this graph in Joule in NEV, then it's not so bad here. We could just have this at minus 4.7. Okay, is the intercept. And then how do we find the slope of the graph? We need to know what F is, don't you? You need to know what that threshold frequency is. Now, work function, they've given it to us as 4.70 eV. If I want to change that to joules, I multiply that number by what? Yes, 1.6 to the 19, to the minus 19, which equals 7.52 by 10 to the minus 19 joules. So now I've converted this to joules, so I'm saying that this y-axis is in joules. This value here, this y-intercept is now minus 7.52. That's our work function. Work function related to the frequency is Planck's constant multiplied by the threshold frequency. So the threshold frequency is equal to the work function on H. Which work function do I use, this one or this one? Why the bottom one? Yeah, that's right, yeah. So we need to have these, the units for these two to be equal, okay? So 7.52 times 10 to the minus 19 over 6.63 to the minus 34. .13, the book says, by 10 to the 15 hertz. Now, I'm not even going to put a scale in here. I'm just going to say, okay, there's my 1.13 and say 1.13, and this is by 10 to the 15 hertz, and then I can just draw in my graph. Copper. Another example. Example 3, the stopping potentials for electrons emitted from a metal by light of 4 different wavelengths are given in the table below. So here's some values where you know what they've done is they've irradiated these wavelengths of light here onto a metal surface, and they've recorded at what point those electrons just didn't make it to the other electrode. 0.33 volts, 0.79 volts, 1.49 volts, and 1.82 volts. Draw a graph of the maximum kinetic energy of the emitted electrons against frequency. So a graph like we just drew, except you're going to have to do some calculations using our formulae. From your graph, determine the following: Planck's constant, work function of the metal, threshold frequency of the metal, and the maximum kinetic energy of the electrons emitted by light of frequency 8 by 10 to the 14 hertz. Now, how will we calculate Planck's constant given a graph? Slope of the graph. How will we calculate the work function given a graph? Y-intercept. You could use the threshold frequency, yes. Threshold frequency. X-intercept. And maximum kinetic energy of electrons emitted by light of frequency 8 by 10 to the 14 hertz. Yeah, that's right. You'll find where that is on your graph, on the x-axis, and then draw a line to it on your graph. Yes. Okay, have a go at that, please. You're going to have. Let's look first at the 4 wavelengths that we're given. 4 wavelengths are 5 by 10 to the minus 7 meters, and frequency is 6 by 10 to the 14 hertz, equals 6 by 10 to the 14 hertz. Quiet, please. Thank you. This one's 4.2 is 7.1 by 10 to the 14 by 10 to the 14 here. 3.4 by 10 to the minus 7 is 8.8 by 10 to the 14. So why am I changing this to frequency for starters? Where are these numbers going to go? They're not the threshold frequency. Yeah, the x-axis, isn't it? 9.7 by 10 to the 14. And so, okay. So everybody knows, of course, how to do that calculation, don't they? We're talking about light, so C is equal to F lambda. If we want to find F, we put C on lambda, and you get these numbers here. Okay. Let's now plot those. So if you're going to draw a graph, you have to label the axes correctly. F in hertz, and I'm probably going to say by 10 to the 14. It's probably easiest. And kinetic energy, I'm going to leave it in EV. Makes for ease of calculation because we're given these stopping voltages in volts. So they correspond exactly to EV. Have a look. Kinetic energy maximum is equal to E multiplied by the stopping voltage. That's in joules. The K max in EV is just E stopping voltage on E. So the E's cancel, we just got the stopping voltage. We'll finish this next lesson. Thank you.